So I'm going to give you a second to go ahead and try to read this to yourself. So pause the video and do that. Okay, I'm going to highlight the important things, right? We've got that this ladder is 20 feet long. It says that the building is vertical. That's a little bit helpful. Most buildings are. If the bottom of the ladder slides away, okay, so that description helps us decide about what to name this rate, okay, horizontally at 2 feet per second. How fast, that's an indication that we're finding a rate. Is the ladder sliding down? OMG, that is really important. The building when the top of the ladder is 12 feet above ground. Okay, so that last little bit tells us when we're making the calculation. So let's try to figure out our given and our find statements here, okay, about our rates. So the first rate that I read, okay, is this 2 feet per second. So I have to figure out what to name that rate, okay? And this much is what we know. It's happening with respect to time. The question is, what do I put, right, in that spot in the numerator, okay? So here's what's happening in this diagram. We have this ladder, which is 20 feet long. That's not a rate, so I'm just labeling it in the diagram. And we've got it kind of sliding down and making, you know, kind of this right angle with the ground if we kind of draw this triangle underneath, okay? So this point where the right angle is going to kind of be like our point of reference here, okay? And that kind of sets it up to look like an XY plane. So any movement along this axis, we're going to, you know, respond with things in terms of X. And over here, of course, this is the Y axis, so we'll talk about things in terms of Y. So if I read that it is changing horizontally, right, that's in this direction, this point is moving away from my point of reference, I'm going to call that dx dt, okay, because of that word horizontal, okay? We're supposed to calculate how fast the ladder is sliding down the building, so that would be a measurement of this point right here, the top of the ladder, and its movement downwards, right, is in the y direction. So that's specifically why I'm calling this dy dt as the rate that I'm trying to find. And then we're doing it when the ladder is 12 feet above the ground. So again, above the ground is a reference to height. So that is y in our picture. So that's y equals 12. Okay? So kind of like yesterday, I've got x, I've got y, and I'm going to formulate an equation from those two values. Okay? It makes the most sense that we would use the Pythagorean theorem, and we're going to do something new today. So we are going to put 20 in our actual equation that we differentiate. Okay? 20 is a different sort of constant than the y equals 12. Okay? Because 20 is kind of representing this z side of this triangle, but it's unchanging. It's not like the ladder is expanding or contracting in length. So since that is a true constant, what we're going to call it, it is allowed to go into my equation to start off with. Okay? And that's good news because then there's no dz dt, right? That side is not changing on that ladder, so I don't have to have another, you know, rate in here to work with. Okay? The rest of this is going to be pretty basic, based off of if you're picking things up from yesterday and the day before. We're going to do d dt to this, right? We're going to get to x dx dt. We're going to get to y dy dt. And then we're going to get 0 over here for the differentiation of 400, basically, right? That's a constant, so that's 0. And now I'm just going to make room for all of my numbers to plug in. Okay? And then I'm going to leave dy dt as my variable because that is what I'm actually solving for, so that stays letters. Okay? Now I'm going to take the information I've been given. Dx dt is going to plug in 2 there. So that is where that 2 goes. X, I'm going to have to do a little work to figure out. And then y equals 12 goes in this spot. Okay? And now what I've got here is I've got, of course, a missing variable. So I'm going to have to work with the original equation to figure out what x should be. So I know that x squared plus 12 squared, that's the moment that we're making this calculation, has got to be equal to 20 squared. So I'm just utilizing that original to solve for x. All right, this means x squared is 256 if I work that out and subtract. So x is technically plus or minus 16, but we're going to use the positive because we're talking about, this measurement here from the wall to the bottom of the ladder. Okay, now I just grind this out and solve for my missing variable. So this component here, right, is 64 plus 24 dy dt equal to 0. And when I go ahead and solve by subtracting 64 from both sides and dividing by 24, simplifying that, I get negative 8/3. And then I'm going to slap some units on here based on what y is measured in and what time is measured in. Y is a unit that measures length, so in this problem it's feet. And then seconds are the measurement of time. Okay? Have a moment to think about why is this answer negative, right, in your own mind. Why is that happening? Okay? If it's describing the movement of the ladder, how fast, right, the top of the ladder is sliding down the wall, it's negative because we are getting closer to this point of reference and we're losing ground in that way, right? So since this is heading downwards, that's why it's going to be a negative answer. And that's why when we assign this value 2 feet per second, since this was moving away from the point of reference, it's 2. If somehow somebody was pushing this ladder against the wall at 2 feet per second, closer to this point of reference, we would have labeled that as negative 2. Okay. All right. So Pythagorean theorem is in play now for further examples in the book and your homework and such. The next example that we're going to do is something with volume. Okay, we did volume of a sphere yesterday, so now we're going to do volume associated with this cone. I'm going to give you a second, right? Go ahead, pause the video and read the problem to yourself, highlight anything important, and start to think about your given and your find. Seriously, see if you can come up with the given and the find on your own. Fill that in now and see how close we are to having the same thing. Hit pause. Do it. Okay, this altitude and this base radius, again, kind of up here just helps me to label. Okay, this total tank is 12 feet tall. Its radius here, this is only 6 feet. Okay, we're going to highlight, right, water is being pumped into the tank at this rate. I'm going to determine the name of this rate based on its units. What do cubic feet measure? Measure volume, Miss Rand. Oh, you're right. Okay, so we're going to call it dV dt based off of that unit of measure, 1.337. Okay, I'm approximating the rate at which the water level is rising when the water is 3 feet deep. So water level in this diagram is h, little h, right? So we're going to find little h here, dH dt, at 3 feet deep, right? Means how full this water is. If it's 3 feet, that's a measurement, again, of h. So we're doing this when h equals 3. Okay? So in case you forgot the volume of a cone, right, that's what we want to use because we've got v here, we've got h here, and we want to be able to relate those two variables. Okay, I'll hook you up. It is v equals 1/3 pi r squared h. Now you've got two options at this point. You can maybe differentiate this guy with respect to time and use the product rule and treat 1/3 pi r squared as the first function and treat h as the second function. However, that's going to have a dr dt in it when you go to differentiate it, so we want to make sure that you only try to work with the variables that you see here, unless you can figure out dr dt by some other means. Okay? So that means that we're going to use these similar triangles in here to write a relationship between r and h so I can substitute out the r variable. So you'll see here by these two triangles that I'm highlighting, whether it's the yellow one or the pink one, those are similar triangles, and that means that, right, their lengths are always in the same ratio, right? So since the radius is 6 and the height of this cone overall is 12, that means every smaller level that this tank is filled up is in the same ratio, where R equals 1/2 of H, right? 6 is half of 12. So this is a little fun fact that will allow me to rewrite this equation. V equals 1/3 pi times 1/2 H squared times H, okay? So I haven't differentiated. I have subbed out R for this value 1/2 H. Now I'm going to simplify a little bit before I differentiate. So this is technically 1/3 pi times 1/4 H squared times H. And that simplifies, right? As simple as you can get it makes it the easiest for calculations going forward. So I'm going to say the actual volume formula that I'm going to use is pi 12 H cubed. And that's what I'm going to differentiate. So you can now pause the video and try to figure this out the rest on your own, or you can keep watching and kind of watch how it goes down. So d dt, right, when I differentiate it, I get dv dt equal to pi 12 multiplies through because it's a constant. Derivative of h cubed is just 3h squared, much better than that product rule. And then I've got dh dt as my implicit multiplier. Okay. And now I can plug in numbers that I have from up above. Okay, 3/12 does cancel out to pi 4, so maybe you will use pi 4 here. dv dt is the given information, right? So that's going to be 1.337. Pi 4 is this value. H is 3. I square it, and then dh dt is what I'm solving for. Okay, so use your calculator to come up with a value for dh dt that's accurate to 3 places. Okay, 3 decimals. Pause the video now, see if you can come up with it. And now, if you did calculate that correctly, you should be getting 0.189. And then, since we're talking about height per time in this, notation, we're going to label this 0.189. Height is measured in feet, and time in this problem is minutes. So we're going to do feet per minute.